Welcome back to The Explainer. Today, we're putting on our systems engineering hats and taking a really rigorous architectural look at a massive structural blind spot in modern AI. Specifically, we're digging into why verifiable reward pipelines, the exact systems driving all these wild breakthroughs in machine mathematics and reinforcement learning, are actually structurally blind to security. If you've ever sat there wondering why a mathematically perfect model still somehow gets breached in production, well, this is exactly why. We're going to break down the Beyond Verifiable Reward white paper. It's an absolutely fascinating analysis of the security layers sitting right underneath machine mathematics.
Think about this fundamental truth for a second. Every capability you want, an adversary wants more. It's just a profound, unavoidable reality of engineering. The literature out there on machine mathematics and verifiable reward is brilliant, for sure, but it is almost entirely a capability literature. It assumes this idealized, indifferent environment, a beautiful world of elegant proofs and isolated search procedures. But let's be real, the systems actually instantiating these ideas do not live in a vacuum. They're containerized. They're hooked up to AWS roles, they're network attached, and they are inherently adversarially exposed. When you build a capability proposal with zero threat model, you aren't producing a neutral design. You're actually producing a design pattern whose very first competent implementation is going to be a literal attack platform.
So here is our game plan for today. We're tracking the math all the way down to the metal, starting with the verification asymmetry, moving into objective space injection, looking at LangSec and Parser differentials, and finally closing out with the mitigation stack.
All right, diving right into Section 1, the verification asymmetry. Keep in mind, we aren't talking about a simple code bug or a misconfiguration here. Look at what happens to theoretical objects when they actually ship to production. In a white paper, concepts like unbounded search or abstraction shifts are these beautiful, mathematically pure ideas. But in a deployed security reality, a mathematical proof just becomes a brittle, hard-coded invariant in your trusted computing base. Unbounded search turns into a localized denial of service attack or a verification exhaustion vulnerability. Theoretical abstraction shifts literally become sandbox escapes, and theoretical equivalence turns right into an exploitable parser differential. The second a theoretical capability meets a real-world hostile environment, it instantly becomes a critical attack surface. And here is the mathematical root of the whole problem. Offense is an existential claim, represented by the mathematical symbol for there exists. It literally only requires one witness, one successful exploit against the real system. It completely self-verifies on execution. It's like finding a single tiny crack in a massive concrete dam. Defense, on the other hand, is a universal claim. For all inputs, this behavior does not occur. You have to mathematically prove that no cracks can possibly exist anywhere under any pressure. But you can't run a universal claim in a production environment. You require a proof against a model of the system, and that model itself is inherently unprovable from inside the system. So functional correctness is cheap. You just need a single witness. But security properties? They require universal quantification over an infinite adversarial state space. This triggers a phenomenon we call assurance deflation. Think about it. Deployed capabilities are accelerating at breakneck speed because existential search, the attacker's job, is incredibly easy to automate. But constructing the model for defense, deciding exactly what an adversary can observe or influence, you can't just automate that. So deployed capabilities scale incredibly fast, while formal assurance scales at an absolute crawl. It creates a terrifying blind spot where your documented security controls just sit stagnant on some compliance checklist, while the system's actual exploitable capabilities move orders of magnitude beyond them. Which takes us straight into Section 2, Objective Space Injection. This is the first concrete exploit class born directly from that verification asymmetry. We have to start with the price of benignity. When you take an architecture optimized for a totally indifferent nature and expose it to an active, bounded adversary, the mathematical optimum shifts. That resulting performance gap is the price of benignity. A smart attacker absolutely leverages this. They poison the training curriculum by realizing that a perfectly benign-looking top-level goal can be mathematically optimized in a way that forces the agent to execute a prohibited high-risk subgoal. Imagine giving an agent a harmless goal like optimize server load. The agent might mathematically deduce that the absolute fastest route to zero load is to intentionally crash a critical redundant node. Let's walk through how an attacker actually pulls off an objective space injection, or OSI. Step 1. They map out the agent's capabilities and its prohibited actions. Step 2. They search the space of totally benign objectives to find one where the optimal mathematical decomposition requires breaking the rules. Step 3, they delivered that clean, benign goal. And step 4 is where the damage is done. The agent's own internal planner mathematically decomposes that benign objective into a malicious, strictly prohibited subgoal. This is exactly why your current defenses are probably failing completely. Subgoals defeat intent-based monitoring at the root. Right now, systems monitor prompt instruction space. They look at the literal text typed in. But in OSI, the dangerous objective isn't in the prompt at all. It exists entirely as an unlogged activation state running dynamically between the agent's tool calls. The safety policy engine gives a thumbs up to the benign request, completely blind to the fact that the agent's hidden objective landscape is about to execute a malicious action. Okay, moving right along to Section 3, LangSec and Parser differentials. We're going to use Language-Theoretic Security to show how semantic ambiguity creates massive structural vulnerabilities. Let's talk about semantic tolerance. It's a parser's ability to accept a bunch of surface-level variations as meaning the exact same thing. And this creates a massive paradox. Semantic tolerance is literally what makes large language model policy engines so usable. They get your intent even if you phrase it weirdly. But mathematically, it makes them fundamentally unsound. You just cannot have semantic tolerance and differential freedom in the exact same component. And that tolerance creates a massive parser differential. This is an exploitable gap where you have a highly tolerant LLM policy engine sitting right next to a totally rigid deterministic code runtime, and they diverge on interpreting the exact same input. Through this gap, natural language inputs essentially get transformed into Turing-complete weird machines. It allows attackers to literally write exploit code using conversational English. The result? A classic confused deputy attack. The attacker crafts a call where the representation evaluated by the policy engine looks totally innocent, but the representation the runtime actually executes is malicious. Authorization is granted against a parsed natural language description, but the actual execution is performed against a completely different operational object. The safety engine gets entirely bypassed, but it leaves this perfectly clean, auditor-friendly paper trail saying the request was approved. So the huge question we have to answer is this. How on earth do we secure pipelines that are structurally blind to their own adversary models? If we can't trust the math the second it touches the real world, how do we survive this verification asymmetry? Let's get into the fixes in Section 4, the mitigation stack. We're going to look at some concrete low-cost engineering controls proposed by the white paper to actually patch these architectural blind spots. First up is the formal library transparency log. It's a remarkably cheap, high-impact monitor that essentially borrows from certificate transparency. It uses an append-only Merkle tree to securely track all library contributions, mandating inclusion proofs so you can cryptographically verify dependencies without downloading the entire log. It also uses a gossip protocol to ensure an attacker can't serve a malicious split-view log. Most importantly, it runs automated monitors to constantly diff the axiom set against a pinned baseline, alerting your security team instantly if any new, unverified mathematical assumptions get injected into the trusted computing base. Next, to stop objective space injection, we have to use subgoal telemetry. Remember, those dangerous subgoals hide in unlogged activation states. So the fix is that planners must emit their intermediate decompositions to be logged and policy evaluated as first-class artifacts. Your hidden objective landscape has to be auditable. But, and this is critical, we don't just rely on subjective human-in-the-loop sign-offs anymore. We have to replace those with comprehension verification. This means running counterfactual perturbation batteries against the logged subgoals to mathematically prove the agent's actual intent before it executes anything. Then, to kill those parser differentials, we enforce strictly bound representation alignment. We have to violently eliminate the semantic gap between the policy evaluation and the runtime execution. You do this by binding authorization strictly to the executed code representations. Crucially, this includes implementing span integrity chunking to defeat RAG evasion, making absolutely sure that retrieved contextual data hasn't been subtly poisoned. The policy engine must evaluate the exact structured code the runtime is going to execute, not just the highly tolerant natural language description the user typed in. Now, I want to leave you with a slightly uncomfortable truth about systems engineering. Testability is attackability. Sometimes we call this grindability. Think about standard CI/CD pipelines today. 15 years of DevOps maturity made our systems beautifully deterministic and testable. But determinism and replayability, those aren't just Defender-specific affordances.
By raising determinism for defense, we accidentally created a perfectly efficient, replayable search environment for any adversary who gets inside. The very tools we built to make our systems safe actually made them infinitely easier to mathematically optimize against. Which leaves us with this final critical question. When the next massive breakthrough in verifiable reward drops, will your adversary model actually scale with it? Or will your rigorously tested, highly deterministic security controls just become another highly efficient search environment for the attacker? You cannot blindly trust ideal proofs in a hostile world. You have to explicitly audit your own adversary models. Thanks for joining me for this explainer, everyone. Keep asking the hard engineering questions, and I'll see you next time.